So I'm going to take us sort of to the other end of the scale from the talks we saw this morning, from nanoscale to some of the largest systems in the world, actually, the electricity interconnections in North America. This is the scale we've been doing this work on. It's really it's a new area of research and engineering. And for those of us who have been around in the renewables business for a while, I often refer to it as being in a luxurious position to start having to actually worry about what if we get a lot of this stuff in the system. So this is, if you're looking at areas of interest that are new and up and coming, certainly the area of renewables and efficiency technology integration and the smart grid, these are all, they're wide open to new ideas and new exploration. I do have the privilege this morning of talking to you a little bit about some of the studies that we've done, and a couple of them that our group has been involved in I really consider to be sort of seminal studies. They're the first of their kind to cover this scale of not only renewable energy penetration, but this scale of systems. So I'm going to talk through those with you in a little bit, but a little context setting first. Well, the outline of my talk, I am going to give a little bit of context, a slide about the National Renewable Energy Lab. I know some of my colleagues have presented already, so hopefully I'm not covering ground that's already been covered. A little bit of context about how we view our role, what we feel like our purpose is in transforming the nation's energy infrastructure. And for those of you who may not have had much exposure to how the power systems operates, it's important to have a little background knowledge about that to understand how we approach the study and what some of the results are. So I'll talk through that for a minute. I know from talking to a couple of you last night, there are several of you out there I know more about the power system than I do. So bear with me while I step through that stuff. I will go over why integration of renewables into the system in large numbers is a problem at all. I mean, it's not immediately obvious to everyone who is unfamiliar with power systems operation why it should be an issue. And then I will go through a few details of a study that we released last year that looked at high penetrations of wind and solar into the western part of the electricity grid in the U.S. So first, just a few minutes about NREL. A lot of stuff on this slide, but the message that I really want to convey is that, well, a couple messages. One is that we are a national laboratory and we view our role in a national context, and we think it's our objective really as the only Department of Energy laboratory focused on renewable energy and energy efficiency to contribute in a very significant and timely way to meeting our energy and environmental objectives in the country. And they're aggressive. This administration has laid out some very aggressive goals by 2050 to reduce our oil use to 15% of what it is today, and to have our carbon emissions reduced by 80%, with a number of intermediate targets to get us there that impact the way we view the world at NREL and the way we operate and how we formulate our strategic vision. 25% of electricity by 2030 from renewable sources, a building fleet that's 50% more efficient, and then I won't go across all of them, but we really believe to do this, a key element in the way we formulate our vision at NREL is that you can't do this piece by piece, part by part. You've got to look at the whole system as an integrated set of smaller systems, and that there has to be a recognition that the introduction of a lot of new technologies into any part of the system is going to impact different aspects of the system up and down, all the way from large central generation down to the power we use in this room. So it's a complex system of systems, and the introduction of a lot of new technologies is really going to necessitate a transformation in the way it's built out physically and the way it's operated. So I'm going to talk through some of those issues with you today. So first, a quick overview of the power system. Right now, this is the way it's structured. There's central generation. You take that generation, typically that's generation is done in the tens of thousands of volts range. You take that voltage, you step it up, you transmit the power over long distances through transmission lines, and transmission voltages are in the hundreds of thousands of volts. The voltage is one of the sort of how you distinguish, one of the distinguishing features of the different parts of the system. You get down to the substation and you step down. The purpose of the substation is to step the voltage down back down to tens of thousands of volts until you get it to the plug in the wall, which is 120 volts. So those are the three basic parts of the system: generation, transmission, and distribution. And talk a little bit about each of them, and why I'm making these distinctions about how they're operated and maintained will become a little more clear later. But the generation part of the system is a part of the system that's actively operated and maintained. Large-scale generation is owned by a variety of different players in a deregulated world, or at least partially deregulated. It used to be mostly all vertically integrated utilities who would own all aspects of the system, but that's changed quite a bit. Generation actively operated and maintained. So there's a great deal of control over the generation. They take contractual orders essentially to know how much power output is needed for a given day, a given hour. And of course, they're actively maintained. And just for a little additional context, this is the current energy mix in the U.S. today. So it's mostly coal, as you can see, nearly half. Up until a few years ago, it was half, but that's been displaced by the additions of a lot of gas and renewables as well. About a quarter gas, about a fifth nuclear, as you can see there, and nearly 7% hydro. And this, just from lack of room, this lighter blue wedge here is the renewable wedge, which is growing. It's visible now. Just a few years ago, that wedge would not even be visible. It's driven mostly by wind deployment. That's the largest scale renewable going into the system today. So we move from generation to transmission. This is another part of the system that's actively operated and maintained. This is where I'll be focusing a lot of the talk in discussing the Western Wind and Solar Integration Study. So I won't go into any more detail right now. And then the distribution system, which by and large is still passively operated or not operated at all, but actively maintained. I mean, it's still, in many respects, the way the system is operated today is the way it's been operated for decades. Not a lot of difference. The control technology, the algorithms used to dispatch generation, to predict the load for the next day, those kind of things have all advanced quite a bit. But fundamentally, this three-component system is operated much the same way it was in 1950 or 1960. And it's remarkable, really, in the distribution system how little visibility utilities have even today into what's happening after this substation right here. Most utilities still don't know if the power's out in a neighborhood until somebody calls them. They don't have any way to see into the system. That's starting to change. There are a huge number of possibilities with smart grid technologies that will allow the system a lot more visibility into the system and allow operators to begin to actively operate the distribution system. I'll talk a little bit more about that in a minute. So just a snapshot of what the transmission infrastructure looks like in the country. These lines here on this map simply show the high voltage transmission lines. It gives you an idea about how distribution, you can tell where there are lots of population centers up here in the upper Midwest and where there are not so many people. So that's what the transmission system looks like today. And I put this up to show that it's broken into three major components: the Eastern Interconnection, Western Interconnection, and Texas. They've got to have their own. In Texas, it's called the Electricity Reliability Council of Texas, or ERCOT. And these all operate, they all have the same power characteristics. So the same voltages come out of the plugs at the same frequency, 60 hertz. But the distinction, why there are three of them, is that these are not synchronized. So the 60 hertz power source here will not necessarily be synchronized with a 60 hertz source here. So there's not, now the only way you can intertie these and have power come in that's synchronized at that 60 hertz frequency is to convert it to DC, put it through an inverter, take it back to AC again, and sync it up with the power system. So this characteristic in itself presents some challenges and some opportunities. For example, one of the challenges is that the best solar resource in the country is over here, but most of the load is over here. So if you wanted to have very long distance transmission, it will likely have to be DC. We don't have very much DC transmission in the country. Or you can convert it and get it across and resynchronize and transmit it as AC. So there are a lot of interesting issues. If you wanted more wind in the west, the wind belt is really here. Fortunately, it's a little bit in both interconnections. So some of the, just to talk about specifically some of the characteristics of the current system that we'd like to address is this is just showing a simple little animation. This system, as I said, is built around central generation, long distance transmission, and step down the voltage to distribute to end uses. It's all about getting power out to the buildings. It's carbon intensive, as you saw. Nearly 3/4 of the generation is carbon-based in this country. And there's a very low utilization of assets. The system is built around meeting a peak that really only occurs for a couple hundred hours every year. You got to keep the lights on during that peak period, and typically most utilities have summer peaks. But that means the rest of the time, if you build the system around a peak, and that only happens a couple hundred hours a year, the rest of the time there you have a lot of assets that are sitting underutilized. So that's something that we like to take into account. There's a lot of congestion at different locations. In the east, a lot of it is actually physical congestion of transmission. There's simply not enough capacity, especially during the peak periods, to get power where you need it. In the west, a lot of the congestion is caused by contract structures. So you'll see kind of sprinkled throughout some of my remarks today, there's a very interesting combination of technical, policy, and market issues that come together to both create opportunities and present challenges. It's an area, that confluence of technology, policy, and market is one of the things that's really intriguing to me, and an area that's really ripe for a lot of new exploration. So there's very limited right now, very limited utility customer interaction. Already alluded to that. You interact by either picking up the phone and calling your utility or waiting for your paper statement in the mail. Certainly we have technologies today that can allow us to have a more interactive system than that. The system is increasingly vulnerable and antiquated. While a lot of the technologies I mentioned, it's operated in much the same way it is for decades. I mean, a lot of the technology and transformers and so forth has not changed very much either. So there are a lot of different ways to visualize a future power system, but then this is just one of them. But certainly the way things are going to be changing, a lot more renewables into the system, and renewables are very modular by and large. Photovoltaics, especially wind, to a certain degree, so they can be interconnected at many different parts of the system, and both interconnected at distribution voltages. In fact, the vast majority of PV that's in the country right now is interconnected at distribution voltages. Most of the wind is interconnected at transmission voltages. I think we'll see in the coming years the introduction of a lot more communication and control technologies, which is just a smart grid is a name for that. Those kind of technologies give you more visibility into the system. You know what the power conditions are at various points of the system, and you can once you know that, you can integrate more controls remotely into optimizing how the system is performing and how the power is getting to the end use. They're coming at some point will very likely be storage. This is one of the great opportunities, I think, technically and from a business perspective. I've heard more than one person say when asked, what might be the next Microsoft or something like that, the next Google. And I really believe that if someone can come up with very cost-effective storage, that could be a very successful individual or company. I'll talk a little bit more about storage and the impact on storage for integrating renewables a little bit later in the talk. Very much a wild card in how the system might get built out and operated is the potential electrification of transportation. There's a lot of opportunities there. Right now, as plug-in hybrids are starting to come on the market, the first ones really in 12 are going to be commercially available. The utilities view those really as a new revenue source. It's new demand. I mean, you're shifting from oil to electricity, but there's also a lot of opportunity for with a smarter grid with adequate communication and controls, for example, to allow a utility operator, if the proper communication devices are on the car, to be able to look into the system, see how much storage they have in aggregate out on a particular distribution feeder, and if necessary, be able to send a signal to all those cars to charge and discharge in a manner that optimizes the efficiency of how the system is operating. You know, of course, the customer would be compensated for those services they provide to the utility, but there's a lot of stuff that would have to be worked out in the market and policy realm to enable that. But right now, if you go buy a plug-in Prius next year, you can plug it in and charge it whenever you want, whether it puts additional stresses on the system or whether you decide to charge it at 2 in the morning. The system's not going to know the difference right now. So a lot of changes. In fact, I'd refer to it already as a transformation in how the system gets built and operated is really going to have to take place to realize a system that looks like this. And then another aspect you see from the arrows moving here that's very different than what happens in the system today. Right now, power system basically flows, everything flows in one direction with distributed generation all over the system. You're going to have power flowing in both directions, which is a fundamental difference in the way it's operated today. So I want to talk to you now that moving out to how the transmission system gets operated and how utilities order the dispatch of their generation fleet to meet the demand. This is one way that not much has changed in the fundamentals and how the system is operated. Utilities really focus on a couple of things in deciding what generation to bring online. They typically look a day ahead. So a utility is utilities all over the country are sitting there today projecting what the demand is going to be tomorrow. Actually, it's a little bit of a bad day because the weekend, everything is different on the weekend. So let's pretend it's Thursday. So they're sitting there, it's Thursday, they're looking at what's going to happen Friday. They use two things really, primarily. I'm vastly oversimplifying, but two things primarily get used. One is what the load was today. They know it's probably not going to change a huge amount tomorrow, with the exception of the impact on the weather. So they look at the load profile today and the weather forecast for tomorrow, and they make an estimate of what the electricity demands on the system are going to be for tomorrow. And so this is an example of a load curve. This is an actual load curve in the Western Interconnection for a large, it's kind of a 5-state footprint that you'll see in a minute in the Western Interconnection. Kind of intuitive what happens here. This is midnight, so overnight the demand is really low. When people start getting up in the morning, it ramps up. Stays a little bit level during the middle part of the day, and then toward the end of the day when businesses and industries are still working, but people are getting home and turning on ovens and drying clothes and all of that sort of thing, is usually the peak is in the late afternoon, early evening, and then it ramps down again as the evening goes on. So they look at that, they look at the weather forecast, and they decide, they develop what's called a dispatch stack. And it's the dispatch of their generation fleet in a way that is going to cost them the least to provide the energy to meet the load, to meet the demand. And this is an example of this exact day in the dispatch stack that was generated. You can see this is 11 April to 12 April. This happens to be 2006, so that's not really important. But what happens here is that there's base load, so-called base load generation. In this case, it's nuclear and coal. So they meet the majority of the power with requirements with base load. For intermediate load, they use combined cycle gas, and to meet the peak, it's hydro. So I needed to introduce this idea of the dispatch stack because some of the more interesting results from the Western wind and solar study that I'm going to show in a minute are related to how the dispatch stacks are affected with a lot of wind and solar in the system. So you can see that the utility has a lot of control in this system. If they're accurate in predicting what the load is, I mean, which is, I'd like to point out, it is variable. Utilities are used to dealing with variability, and it's somewhat uncertain. They don't know exactly what the load is going to be, so they already deal with variability and uncertainty on the load side. They are able to dispatch generation to meet that demand. So what happens, though, if we introduce variability and uncertainty on the generation side as well? Well, that's what introducing wind and solar into the system does to a utility. So it really changes the game for them, and I have a couple slides to illustrate. This is the output of a 100 megawatt wind farm over the course of 24 hours. And the challenge for utilities then is they can't control that. The wind blows when it blows. I mean, if they need more gas power, you put more fuel in, you get more generation. If they need to turn it down, you withhold fuel, reduce the generation. In this case of the 100 megawatt wind farm, the wind is both variable and uncertain. So you'll notice, by the way, that I typically don't use the term intermittent because there's sort of a reliability connotation, I feel like, in the word intermittent. And wind and solar plants generally aren't intermittent. We can predict with pretty good accuracy under a given set of conditions what the output's going to be. But they are variable. You can see here, it's starting out overnight. It's producing a little over 70 megawatts. The wind ramps down toward dawn, and then eventually, somewhat erratically, works its way back up to producing near capacity overnight. So utility has to deal with that. So what about solar? I mean, if it were never cloudy, this is what the solar resource would look like, and it wouldn't be a problem. These are the three main components that we use to predict the output of photovoltaic or concentrated solar power plants. But in reality, many days are like this. So this is a really classic summer day in Colorado. This is data from the lab. Crystal clear morning. This is the full sky image, but clouds roll off the mountains in the afternoon, and suddenly your resource, the fuel that's being input into the generators is quite variable. And challenge for photovoltaics especially is that in a small system anyway, like if you had a rooftop system on your house, this event here, when this cloud moves over, your system is nearly switching on and off with the cloud movement. So that's a real challenge for utilities. Historically, though, there has not been enough penetration really to cause a problem. I mean, this kind of variability and uncertainty for renewables in small numbers is really just sort of absorbed. It's in the margin of error of predicting the load, in fact, and so utilities haven't paid it a lot of attention. But it's changing now. We are in that luxurious position of having a great deal of deployment happening, especially in wind. Solar is ramping up. There are billions of dollars worth of concentrating solar power projects that are in the works, getting permitted, getting built. So a lot of renewables coming online. And in certain areas of the country, it's already becoming an issue, this variability and uncertainty. Colorado is one of them. Texas is one. Certain places in California, they already see issues. In Colorado, for example, we have about 1.3 gigawatts of wind on what is not a huge system. Colorado is not a hugely populated state. So I want to talk a little bit now about the studies that we've done. We've done several now. These are just two examples. These are the biggest ones. The Western Wind and Solar Integration Study, which looks at the Western interconnection, and the Eastern Wind Integration and Transmission Study, which looks at high wind penetration, only wind, into the Eastern interconnection. I'm going to focus in on this one here because I have to pick one. Don't have time to go through both of them. So what we did for this study is we had there's a consortium of utilities that make up a footprint in the Western interconnection called WestConnect, It's a kind of a market collaboration in the Western interconnection. Well, the WestConnect utilities came to us and said, what if we had high, can we operate our system if we do have high penetrations of renewables along the lines of what many portfolio standards are calling for, something in the 20 to 30% range penetration. So we undertook this study with funding from the Department of Energy in close collaboration with all the stakeholders in the Western interconnection. So the Western Electricity Coordinating Council, all the utilities in WestConnect, people from the Federal Energy Regulatory Commission, from the North American Reliability Corporation. So all of the folks who have an interest in the operations and reliability of the Western interconnection were part of what we call a technical review panel. And I emphasize that a little bit because it's a critical part of these studies. We couldn't sit in cubes at NREL, develop a big study, throw it out there, and say, hey, look at this. This is the story. We had a lot of buy-in on the front end from all these stakeholders in what assumptions we made, what modeling techniques we used, and picking penetration levels and how we were going to interconnect those hypothetical plants into the system. All of that stuff was a consensus on the front end, so that the results of the study on the back end sort of have a good deal of acceptance built in. So the fundamental question that we ended up asking is, can we operate the WestConnect footprint and the Western interconnection with 35% wind and solar penetration? Now, when I say 35%, a couple of qualifiers on that. 35% means on an energy basis, not on a capacity basis. So the actual 35% of the actual kilowatt hours provided in the system come from wind and solar. In the high case, it's 30% wind, 5% solar. And I forgot the other point I was going to make. But in addition to the question, can we operate 35% renewables, there are a lot of other questions once we model the system to be able to do that and start looking at how the system reacts to this level of penetration. It's a lot of other questions start to come to light too. We start to get insight into a number of other things about if we build the system out so that we maximize the best resources and get those resources to the load with long-distance transmission, or is it better to build lower quality resources by the load? We're able to look at those questions. We're able to look at the issue of contingency and operating reserves, and is storage needed? Does geographic diversity help? And also, we were able to run different cases for different accuracies of resource forecasting. The utility operations demand a whole new level of solar and wind forecasting than what we're accustomed to just monitoring the weather, if it's going to be a good day to be outside or to fly a plane or whatever, which is what the weather's been typically used for. But they want to know what's the wind going to be like at a wind site tomorrow for every hour of that day. How's it going to change? And then when you move into that day and you're actually operating the system, they want to know what's going to happen in 15 minutes. What's going to happen in 10 minutes or the next hour. So a much higher temporal and spatial resolution forecasts are going to be needed to operate the system. So the study methodology, just a very high-level overview here. This is the way we approached it. We first developed high temporal and spatial resolution resource data sets, both wind and solar. And in fact, we developed data sets based on physical operations and then modeling from that point. For wind, for 3 years, 2004, 5, and 6 were the study years that we used. We have wind data sets on a 2-kilometer grid for every 10 minutes. So that's a large data set for every 10 minutes of the year for 3 years on 2-kilometer grids for the entire western U.S. Solar is a little less high resolution. It's on 10-kilometer grids for every hour, but we ended up doing some different modeling work to extrapolate down to 10-minute intervals for solar during times of real interest, during high ramp times for the utility. So then after we had these data sets, we know where the good resources are. We hypothetically sited plants and projected their output so that we would know that we were meeting the penetration levels that we wanted to model. Then we interconnected those plants into the Western interconnection the way it's projected to look in 2017. So even though we don't think 35% penetration is a realistic number for 2017, we thought that the system configuration in 2017, because the WEC, the Western Electricity Coordinating Council, does a rolling 10-year projection of load growth and subsequent capacity expansion for the system. We thought that was a very realistic look at what the system might look like. And we started the study in 2007, so this was the farther south that WEC was going. So we interconnected that into the 2017 Western interconnection as WEC thinks it would be. And then from that, we conducted the operational analysis for the high penetration scenarios and quantified the challenges and benefits. So an important point about this really is that one quite unrealistic thing, you're confined to how many variables you can manipulate in a study like this. So we took that 2017 build out and simply overlaid the renewables. So the system is overbuilt in capacity terms by the amount of renewables in the system. So just to give you an idea about how much resources are in the West, they're enormous. Our renewable resources, if we can figure out how to operate the system with them, is they go well beyond what our current and future projected consumption would be. Every one of these dots, for example, these are the hypothetically sited wind plants, represents 30 megawatts of wind. Many terawatts of wind capacity could be built out here. And then solar, every one of these dots represents 100 megawatts of solar. So the combination far exceeds if all of these sites were built out, far exceeds our electricity consumption currently. We did multi-dimensional scenarios here, and I'm not gonna spend a lot of time here just for time's sake. But one of the things we did, we modeled the system and ran the models for the 3 years at different penetration levels to see where different issues started to become introduced into the operations. And as I think I mentioned before, in this high penetration case, which is where I'm going to focus the rest of my remarks, it's 30% wind, 5% solar. Of the solar, 70% is concentrating solar power, which is a solar thermal technology, and 30% is photovoltaics. And to reach this level of energy penetration, it requires about 75 gigawatts of solar and 75 gigawatts of wind, 15 gigawatts of solar. So a lot of wind and solar, much higher levels than are in the system today. So another dimension to the matrix of the different modeling runs that we did are in how we distributed the build out. We had 3 cases: the in-area scenario, where each state in the West Connect footprint produced enough wind and solar to meet the 35% requirement on their own. What we call the mega project scenario, where only the very best resources were built and transmission was built out to get it to loads from there. So you can see the size of the circle. The blue is wind, the orange is solar, represents the amount of capacity. So you can tell in West Connect where the wind is. Wyoming, incredible wind resource up there. I've seen, I should have a picture come up, but I've seen a funny picture of a very heavy gauge chain and it's standing straight out, and it says Wyoming windsock. And it's desolate up there and and very windy. I've got friends that live up there, and the wind blows all the time. And you can see if we were going to build out the best resources, Wyoming is a tremendous wind resource. And then the local priority, which is kind of a hybrid of the two. So most of my remarks about results coming up are in the high penetration case, 35%, and in the local priority scenario. So remember, the utility operator's job, the transmission system operator's job, is to look at the load from day to day and dispatch generation to meet that demand. And so in the no renewables case, it's the top line that the utility operator is concerned with. But we're concerning ourselves now with net load, which is the load minus the wind minus the solar. And we refer to it that way because, as you'll recall, I talked about least cost dispatch. Once you have wind and solar in the system, the fuel is free, so you always want to take the wind and the solar. Whenever it's physically possible to operate the system, it's a free fuel, so you take the wind and the solar. So additionally, you have no control over when it generates. So we view that as a variation on the demand. So now, in this case, this is July of 06 in our modeling year. Instead of operating to this top line, the utility is dispatching the conventional fleet to meet the demand that's represented by this bottom blue line. And you can see in this week in July, it's not much different. It's fairly periodic. The shape is roughly the same, so this doesn't present much of a challenge. It's because of two things. One, the demand is really high, and the wind isn't blowing very much in this week in July. So I picked this on purpose, of course. This just illustrates in a kind of a calm week what the utility would face. This is still annualized 35% penetration levels. So what happens if the situation is different? And so then in addition to picking one of the easiest weeks out of the 3 years of the study, this is the most difficult week from a utility operator's perspective. You can see the demand is quite a bit lower, 30 gigawatts instead of over 50, 30 to 35 gigawatts, and the wind is blowing a lot. So this presents a lot of different challenges. While the penetration level is 35% on an annual average, you can see that on this day, April 15th, the wind penetration actually exceeds the amount of demand that you had overnight. So it's actually more than 100% penetration on an instantaneous basis. So the utility has to plan for this. And so how do you dispatch? I mean, dispatching to this feels very familiar. Dispatching to this, not at all. And so I want to show this is the dispatch stack for that week. This is the no wind and solar case in the week in July. Looks very much like the dispatch stack I showed before, very conventional. And however, when you introduce this level of renewables into the system, I'll come over here so those folks can see the good chart. We jokingly refer to this as the heart attack chart for the utility operator. It's everything about it really is different. They don't have the same periodicity. The conventional units have to operate in ways that they were not designed to operate, and certainly in ways that utilities aren't accustomed to operating. This is the way they like to operate coal. This is the way they like to operate the nuclear plants. And when you have this much wind and you're taking it on a least cost basis, it really changes the way you have to view your operations. Now the good news is the model shows, and we modeled every single generator, every transmission line in the Western interconnection. So it's a large model with a lot of data coming into it. The good news is that you can operate this system. These coal plants are not ramping or turning down in a way that's outside their operating specifications. So they can do that. Whether you want to or not is a different matter. I mean, for example, if coal plants are designed to function this way and you start yanking them around like this, utilities are already seeing in areas of high wind penetration some significant increases in their operation and maintenance costs. The times they have to take the plants down for operations increases, and we suspect, I think for good reason, that the lifetime of these plants is also going to be impacted. So this is what this really captures here, this dispatch stack on the right, what the fundamental challenges of going to higher and higher renewables. So you could imagine if we were at 50% wind or 60% wind, the problem only gets compounded. If we have dispatch stacks for those different penetration levels, and the real transition to something that looks familiar and looks very manageable to something that's a lot more alarming for a utility operator happens in above 20%, somewhere between like the 25 and 35% range, where it really starts to cut into the coal this way. So some of the benefits, I've talked to you about some of the challenges, and keep in mind that these economic numbers this was purely an operations study. We didn't try to optimize the generation fleet. We just overlaid it right onto the 2017 build-out plan. And we don't account, except for in deciding how to structure the different geographic scenarios, the operational costs don't take into account the capital costs required to get the technology in the ground to start with. So these are purely assuming once it's there and operating, what are the costs, what are the operational cost impacts? And for the high penetration case, you save in fuel about 40%. 40% of your cost of fuel are saved, and it equates for the cost numbers we assume to about $20 billion a year in the WestConnect footprint. So real money, $20 billion saved in the 35% penetration case. And this does assume, we assumed in the study, a cost of carbon of $30 a ton. So it's actually a combination of fuel and carbon cost savings. When we started the study, the price of natural gas was really high. In fact, it was over $10 a million BTU. Now it's down around $4, so it dropped pretty significantly from when we started the study. So the group agreed on an assumption of gas prices of $9.50. So that's much higher than they are today. And an interesting thing happens in the displacement of conventional generation, very sensitive to the prices of coal and gas. And if the price of gas is high, the renewables displace gas generation, which doesn't emit as much carbon as coal generation. So the impact on your emissions is less than if gas prices are low and coal is offset. And so this graph shows the difference here. If gas is more in the range of what it costs today, $3.50, you save in this high penetration scenario about 45% of the carbon emissions in the Western interconnection. So a really significant reduction in carbon emissions. There's some controversy about this that really, because of my time, I'm actually not gonna talk about that, about some of the studies out related to carbon impacts of high wind penetration. So geographic diversity, to spend a second on this, this is a real key factor in being able to integrate. You can't look at plants over a small area and believe that is a good representation of what you're going to have to deal with if you have a well interconnected system with plants dispersed geographically. I mean, you could imagine if I'm looking only at that 100 kilowatt plant, it was kind of all over the place. But if I have 100 megawatt plants that are very geographically distributed, the wind may be picking up in one place while it's ramping down in another. And so we looked at that geographic diversity and quantified it. You can see here that this is the New Mexico balancing area here, and that within that small footprint, these scatter plots are over the whole 3 years of modeling. And the farther away you are away from the zero line, the more variability you have. So you can see that if you're looking at a small footprint, you have to deal with quite a bit of variability. Even worse in the western Colorado balancing area, you can see a great deal of variability here. But as you begin to expand the footprint, there's a dampening effect on the variability, and we were able to quantify that. This is looking at just the WestConnect footprint, and this is looking at the entire Western interconnection. So the same thing applies to solar that we're quantifying as well, that if you have geographically diverse sites, then the variability overall is mitigated. Do we need more storage? We only looked at storage in this study on an arbitrage basis. Could we pay for additional storage into the system if we filled the storage up when energy was cheap and sold it back into the system when it was expensive? And a couple of key things that we found here. At the 35% level, we were able to operate the system in the model without adding new storage. There was increased usage of existing pumped hydro storage in the study that was caused by the higher penetration, but we didn't have to add it for operational purposes. And we couldn't even force the model to build storage on an arbitrage basis. It never paid for itself in this configuration. As you get to higher penetrations, that's probably going to change. And storage can have a lot of different functions. It's not just bulk energy storage and delivery, but it can be used for a lot of different things. It could be used for smoothing of a solar plant, for example, and that's on scales of seconds or minutes. It could be used for regulation services. So none of that stuff did we examine in this study. Do we need more long-distance interstate transmission? We definitely need more transmission to get good wind and solar resources to load intrastate, but we found that we didn't need a great deal of new interstate transmission for a couple of reasons. One is that we assumed in this there were no contractual restrictions on the transmission, which isn't the case at all in the West. It's actually a big problem for integrating renewables. We have a lot of transmission capacity in the West that sits underutilized because it's contractually obligated. They have to leave it in case the contracted party needs it. So we assumed in all of our modeling that none of those contracts existed, and that's another key factor. Impacts on reserves. This is just an interesting graph of the ERCOT system when showing the need for reserves. This is the frequency. This is what happened to the frequency when 2 nuclear units tripped offline at the same time. So they lost 2.6 gigawatts of generation. Causes the frequency to take a dive, and they have to recover from that, or there's a cascading effect in the system and you have a blackout. So this is why you need reserves online. What we found for contingency reserves, which is what this is that we were able to, in the worst week in April, and that week that we showed, in the highest penetration case, we were able to always serve the load. So we always kept the lights on in the model, but there are regulatory requirements for having contingency online, contingency reserves, and we were not able to meet those for on average about 89 hours a year. So this is an area for future exploration. Is how do you meet your contingency reserve requirements without building new generation and leaving it spinning 24/7? And we think a lot of that could be enabled through a smart grid and more robust demand response, shedding loads and paying customers to shed load when the time comes, instead of leaving generation spinning. So just in conclusion here, we did find it operationally feasible to go to 35% penetration with some big ifs, and I have them listed here. You have to increase the balancing area cooperation. I didn't talk much about balancing areas, but a balancing area is just a fixed geographic area where generation has to meet demand within that geographic area. There are 39 of those, 37 of those in the West right now. We modeled this as 5 large balancing areas. So that kind of geographic diversity and geographic cooperation will become key in integrating renewables. We have to move away from this contractually obligated transmission. You have to go to sub-hourly scheduling. Right now, when they do the dispatch stack for the next day, that intermediate generation that follows the variability in the load is dispatched typically hour by hour. A couple things that hurts is that the wind and solar don't change hour by hour. They change within the hour. So if you can dispatch your conventional fleet on a sub-hourly basis, you can follow the wind and solar a lot better. You have to use high-resolution forecast. In fact, we ran these scenarios with no resource forecast, and because we had the data sets, we were able to build in perfect forecasts for the next day, and then different levels of forecasting accuracy. You're basically going from no resource forecasting to state of the art, which is what some utilities are using today. Saves $5 billion a year in fuel and reserve cost in the Western WestConnect footprint. So that's on top of the $20 billion you already saved in fuel and carbon. So, and I made this point before, if you knew you were going to have this level of penetration, you would likely build the system out in a very different way. Flexibility is really the key, and I'll kind of close down with that, is that because in these high penetration cases, you're introducing variability and uncertainty onto the generation side of the equation, flexibility is really going to be the key to the future system. A lot of people talk about storage as being the answer, especially if you go to storage conferences. The storage has got to be the answer to integrating more renewables. But I think one of the things that we demonstrated in this study, even though I think it probably introduced more questions maybe than it answered, is that we showed there are a lot of techniques, and a lot of them are based in market and policy issues that we can pursue before that, and we can keep, I think, moving that threshold of penetration up and up using those kind of operating and market and policy techniques that will enable us to integrate more renewables into the system before storage is needed. I think storage is going to play an important role at some point in the future, but right now, as was pointed out in an earlier talk, cost is the big issue. I mean, we have technology and control techniques and all that. If storage was cheap enough, it would be an easy answer. You would integrate it into the system and smooth out all of the wind and solar generation that way. But because it's not cost effective at this point, what we're working on is to find ways to make the system more flexible, to be able to accommodate more renewables and allow us to meet our energy security and environmental goals that we have in the country. So thanks a lot for your attention. I appreciate it.
So questions now for Dave?
You spoke a lot about basically building thousands of megawatts of new generation, new transmission lines to allow for geographic diversity.
Right.
And of course, many of these plants are going to be built by independent power producers, third parties who have to make a profit, and there are huge capital costs here.
Right.
Yet you also based, or it seemed like one of your major assumptions was that the marginal cost of a renewable megawatt was zero because the fuel is free, but there are these capital costs. How do you justify that?
No, that's right. I mean, because this was purely an operational study. If you look at it, we make those caveats. We just have the going in assumption. The WestConnect utilities didn't want to try to do a capital cost or a feasibility or optimization study. They wanted to assume that it was in their system already and look at what the operational impact. So that's the only justification. I mean, we certainly appreciate that the stuff is not going to just appear. It requires a very significant investment. But part of what we did was quantify the monetary operational benefit so that can begin to inform then how much capital investment would be reasonable to realize that level of build out.
So the assumption is not that the renewable megawatts are really free, but just that the utilities are taking all the megawatts they can for some other reason.
Yeah, they're taking, and there are times, just not time to go into this level of detail in some respects, but there are times where wind is curtailed about 1% of the time altogether. It doesn't make economic sense in the dispatch to take the wind, so there's wind curtailment. One of the recommendations in the study, too, is a policy recommendation, regulatory recommendation, is to require wind producers, independent or otherwise, to supply down reserves to stabilize the system in those high wind, low load cases. So that's, there's, I should have put up, actually I forgot to put the links of the study, but if you go on and Google them, you can read the 300-page study, or you can read the 80-page executive summary, which is the one I would recommend.
You mentioned that you couldn't get your model to build more storage just for price arbitrage purposes.
Right.
Two questions there. Did you assume locational marginal pricing in all of the balancing areas that have it? And then, second of all, what did you see in general in terms of peak-off-peak price spreads? What were the trends as you had increased penetration of renewables?
Well, I don't think I'm going to be able to answer the second one off the top of my head. I just don't remember. But their locational marginal prices were considered in the areas where they have. Yes. Oh, you want to go ahead, Stuart? I'll let you.
Given that the eastern seafront is a lot more energy sucking, was there any difference in the study between the eastern and western interconnect?
Well, some of the objectives of the studies were different. The Eastern study was explicitly looking at what kind of transmission build-out would be required, which is highly sensitive, very political issue, because nobody wants to build transmission through their neighborhood. But so that was one of the big differences of the study. Very detailed analysis of transmission capacity expansion in the Eastern study. We did find, and we went up to 30% wind penetration in the Eastern study, and the same finding we had was that it's operationally feasible to do it, but it requires, there are a number of assumptions required to make that happen. But no fundamental technical issues to operating the system with that level of penetration. In the East, it was, the transmission did two things. One of the things we learned from that study was that a significant build-out of transmission, which really was required in the East to accommodate that much wind, did two things. It allowed you to access remote resources, that was one, but somewhat, not entirely, but somewhat unexpected benefit is by having more transmission and better interconnecting the system, it introduces a lot of additional flexibility, a lot of that geographic diversity, and that is one of the things that would be required to realize that level in the East. Oh, I can't remember. Go ahead.
Yeah, so one thing about building new transmission lines, it seems like there's definitely a overlap in the benefits between new transmission lines and energy storage. So in your opinion, maybe this is not an appropriate question, but how much do costs need to come down for energy storage, or sort of competing with sort of building new transmission in terms of adding flexibility to a system like this?
Well, the numbers that were given earlier today, I think, are in the range. That $100 a kilowatt hour, and that's not $100. Just to be clear, not $100 per kilowatt hour of dispatched energy, but of capacity there in the battery. So that I'm not sure what that equates to actually in a kilowatt hour kilowatt hour delivered. But I think that is the range. That
so factor of 5 cheaper, so it makes
yeah, factor of 5 or greater cheaper. But it really could kind of be the holy grail of integration. If there's very little storage in the system right now, so at any instant in time, generation has to meet demand. Yes?
A question about that finding that you were able to meet load all year, but not spinning reserves
Right.
requirement. Did you, I mean, maybe this is just from your personal sense of it, but did the study sort of look into at all how to meet those extra 89 hours of operating reserves without, building another coal plant? And
Yeah.
especially given that hopefully 35% is just kind of a minimum, and that problem will get worse and worse as we...
Right, no, and it would get worse with higher penetrations. But the requirement right now is that you have to have 6% of your demand at any point available in contingency reserves. 3% of that has to be spinning, and 3% doesn't. So if you want to meet those reserves, you have to add additional spinning reserves to do that. You don't know when those 89 hours are going to occur is one of the challenges. So you have to spend them 24/7, 87, 60 hours a year, which is very expensive. So we look specifically, and what we're looking at in the next phase of the study, one of the things we're looking at in the next phase of the study is how you can use demand response. There are already some demand response programs in the country. I mean, Texas, for example, they had a big, kind of an infamous large wind event before they had forecasting in the operations in ERCOT. There was a really significant down ramp in the wind output, and they employed at that point their industrial demand response contracts to stabilize the frequency. So they basically contact the people that they're under contract with to have them shed load. And our argument in the study, our conclusion in the study, is that that's a much more cost-effective way, because you only do that when you need to. You don't have to keep it on spinning, burning fuel 24/7.
We have time for one more question.
Have you guys looked at integrating renewables in transmission-constrained load pockets?
In the Western study, we modeled the PV as distributed PV. But basically what we did is we took the output from that PV and considered it really only at the substation. So we haven't done that. We haven't done that level of modeling. Our group at NREL is working on the distribution side of the equation as well. We're going down, while these are sort of interconnection, very large studies, we're working with utilities sort of feeder by feeder, looking at the impact first on high penetrations of PV on a particular feeder, what that does to the power quality in high penetration cases. But one of the things that we're starting to do, though, is starting to work across those different interfaces to explore that exact question. What happens if I have a very high penetration of PV in an area so that I have backflow up to the substation and out into the transmission system? How do you operate that system, and what challenges are there, and what positive impacts are there in that kind of distributed generation?
Thank you. Will you join us for lunch?
Yes.
So they will join us for lunch. Any other questions you might have? And that's it. See you back there at 1 o'clock.
Thank you.